When news breaks that warehouses full of rare books are being destroyed, our first instinct is to imagine arson or corporate malice. We picture villains burning history for no reason other than greed. But in the world of artificial intelligence, this destruction was not an act of rage, it was a spreadsheet calculation. The decision to burn these physical artifacts came down to one brutal engineering fact. It cost more compute power to teach AI models how to read them than their digital value could ever justify. We are witnessing the first era where cultural heritage is being lost because saving it digitally for machine consumption proved too expensive in terms of GPU hours and hardware economics. To understand why this happened, we have to look at what happens when an artificial intelligence tries to learn from a rare book. Standard large language models are trained on clean text tokens. They eat words like the, and, or complex code syntax with ease because the data is already parsed into machine-readable formats. But rare books often contain handwritten scripts, archaic calligraphy, dense illustrations, and marginalia that defy standard parsing tools. When an engineer tries to train a model on these documents without relying on optical character recognition, they face what we call OCR-free training bottlenecks. In this scenario, the system cannot simply read text. It must process raw pixel data at high resolution to visually interpret characters and context that no standard OCR engine can reliably capture. This shifts the workload from simple token processing to massive visual reasoning tasks. The math here is unforgiving for practitioners in the field. While inference costs, the cost of using a model, have dropped 5 to 10 times annually due to algorithmic efficiency, training costs for complex, non-standard image-text pairs have not followed that same curve. Processing high-resolution images for visual reasoning requires exponentially more floating-point operations per token than processing plain text. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Imagine the difference between typing out a typed letter and trying to decipher a handwritten note in a language you barely understand without any reference guide. The latter takes significantly longer, even with advanced tools. For AI training, this translates directly into GPU hours. If a dataset contains rare books where 30% are legible via standard OCR, but 70% require visual interpretation, the compute required to train on that remaining majority is so high that the resulting model improvement often fails to justify the expense. This brings us to the reality of data frugality in modern software engineering. There has been a significant shift in how teams approach dataset scaling. The consensus among practitioners is moving away from more data equals better models, toward understanding diminishing returns on investment. When engineers evaluate whether to include a rare book in their training corpus, they are not asking if the content is historically valuable. They are asking about signal-to-noise ratio and return on compute hours. The insight here is that adding a handwritten page from a 300-year-old manuscript might improve model performance by less than 1%. In contrast, ingesting standard text corpora yields massive gains for a fraction of the cost. When the engineering team runs the numbers, they see that to process and interpret these difficult assets requires 10 times more GPU time per byte than standard data sources. If the marginal utility of adding this complex data does not match the exponential increase in hardware costs, the rational business decision is often to discard it entirely. This creates a paradox where physical destruction becomes cheaper than digital preservation for machine learning purposes. It is not that companies do not want these books. It is that the current pipeline architecture has no cost-efficient way to interpret them at scale without sacrificing model accuracy or blowing through budgets. The industry has yet to solve the problem of processing non-standard text efficiently enough to make every unique artifact a viable training asset for general-purpose models. We are seeing this play out in system design decisions where data curation is treated as an optimization algorithm running on physical assets. If your pipeline requires excessive compute to process an asset that adds negligible value, it represents a system failure or a business case failure. The destruction of these books was not a mistake. It was the output of an economic model optimized for hardware efficiency and training speed. For developers and data engineers watching this unfold, the lesson is profound. You do not pay for bytes in AI engineering, you pay for floating point operations required to make those bytes useful. Understanding the cost of interpretation versus storage is now a critical skill. When evaluating new data sources, especially complex ones like handwritten archives or specialized scientific diagrams, you must calculate the full compute overhead before committing resources. If your pipeline requires massive GPU time to process an asset that yields minimal performance gains, it is not just technically challenging, it is economically unviable in the current hardware landscape. This reality forces a hard trade-off between preserving history and building efficient models. As long as visual reasoning remains computationally expensive compared to text tokenization, rare books will remain low-signal data points that are too costly to include at scale. The engineering community must now decide if we can invent new architectures that lower the cost of interpreting complex visuals enough to save these assets without breaking our budgets. Until then, the economics of hardware dictate which parts of history get saved and which ones burn. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.